Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Bayes' Theorem and such, and reminding you to please be an active learner as you're watching this video. We're going to talk about the rule of total probability and Bayes' rule during this time, and we're going to change notations a bit here as Sullivan does. And so we're going to use intersect. E intersect F is going to represent the events E and F, and E union F represent the events E or F. We know there's a big difference between and or, and these are just math ways of saying and or. And we're going to restate using this new symbols some rules we had before. So remember, if we had disjoint or mutually exclusive events, the probability of the or of all of them is the sum of the probabilities. So the probability of the union of all of them is going to be the sum of the probabilities because there are no overlaps. And the general multiplication rule, instead of saying the probability of E and F, we're going to say the probability of E times the probability of F given E. We're going to say the probability of E intersect F. So let's begin with a problem. Suppose there are two urns, and think about an urn as being just a big jar. So urn 1 contains 4 black and 3 white balls. Urn 2 contains 4 black, 7 white, and 2 red balls. And suppose that we roll a fair die. If the die is a 1 or a 2, we randomly select a ball from urn 1. However, if the die is a 3, 4, 5, or 6, we randomly select a ball from urn 2. What is the probability that the ball we pick is black? So the approach is we define events as follows. These are the two urns, and B, W, and R are black, white, and red balls selected. And there's a big lesson here. The picture is worth more than 1,000 words. So drawing the pictures can make a lot of sense, and even in problems where I don't draw the picture, I might encourage you to think about that being a good approach. So we're drawing a picture and encoding the data here. So you see, given the roll of the die, we will pick U1 if it's a 1 or a 2. Well, that's 1/3 of the time, and that means 2/3 of the time you're going to pick U2. And that's the first thing you do. You pick one of the urns after you roll the die. But then you have different kinds of things. So here you have 4 black and 3 white in urn 1, so that means the probability of drawing a black from there is 4 out of 7. The probability of drawing a white out of there is 3 out of 7. Here you have 4 black, 7 white, and 2 red from the 13 balls, and so the probabilities of getting black, white, and red are these. So you see, the probability of black in urn 1 is you do urn 1 first and then black, and so you multiply those two numbers together, you get this. The probability of black in urn 2, so you got to go urn 2 first, and then you do black, so you go up here, you multiply those probabilities, you get this. So the probability of getting black is the sum of those two because those are disjoint events. You either land up here or you land here. You don't land both. So you add those two probabilities, and you can use a calculator, and you can say that the probability of black then is 36/91, or approximately equal to 0.396. Now we're going to generalize that a little bit with theory, but again, I encourage you draw a picture. Can be fine. So if we split this space, the universal set, into A1 and A2, and then we take any set E, E has a piece of it that's in A1 and a piece of it that's in A2 because those are disjoint sets. So the probability of E is the probability of the piece that's in A1 plus the probability of the piece that's in A2. Again, those are disjoint events, and the probability of E in is going to be the probability, and this is just using for this one and this one, we're just using the general multiplication principle, and so we get the probability of E is the probability of A1 times the probability of E given A1 plus the probability of A2 times the probability of E given A2. So, again, the picture is better than memorizing a formula, but you see either you go up here or you go down here. And if you go up here, so the probability of E is, you can be up here or here and land in E, but there are two different paths to get there. So this is the probability of path 1, and this is the probability of path 2. And you add them together because they're disjoint. And that works even if you had 3 or more sets. You just draw a more and more complicated picture. But the probability of E is going to be one path to get to E is up here. A second path to get to E is here, and a third path to get to E is here. You take them all together and you add the disjoint components together to get the probabilities. So here's another problem. So suppose a calculator manufacturer buys integrated circuits from 3 different suppliers, supplier 1, supplier 2, and supplier 3. Based on past experience, it is known that 2% of the circuits from supplier 1 are defective, 1% of the circuits from supplier 2 are defective, and 1.6% of the circuits from supplier 3 are defective. So the calculator manufacturer buys 20% of its circuits from supplier 1, 35% of its circuits from supplier 2, and 45% of its circuits from supplier 3. What's the probability that a randomly selected integrated circuit is found to be defective? Okay, well, first thing that we're going to do is we're going to write all that information down in the language that we understand. So the probability of S1, the supplier 1 is 0.2. Probability of getting one from supplier 2 is 0.35, and the remaining 45% come from supplier 3, and these are the probabilities of defective across those suppliers. So you see, either you get them from one of the 3 suppliers, so the probability of defective is it could come from supplier 1, supplier 2, supplier 3, but those are all disjoint sets. And so the probability of a defective is the sum of these 3 probabilities, and then we'll use our probability rule on each one of these, there, here, and here, and do the calculation, and we get 0.0147. So that's the probability that the integrated circuit is defective is 0.0147. You should make sure you understand these calculations. And just in general then, we say that a space is partitioned into n subsets, provided that, and we're basically just break the set up into n disjoint sets. Now we don't allow any of these to be the null set, so we split it up in that, but they're all disjoint, and they add up when you take the union or the OR to S. So we summarize this discussion and this definition with the rules of total probability. So suppose you have E as an event and a subset of a sample space S, and let these be a partition, a disjoint breaking up of the sample space. Then probability of E is given by this sum, because these are the probabilities that is in all of each of those disjoint spaces as shown up here. Now, that might be complicated, and I like what Sullivan does with this. In other words, the rule of total probability can be thought of as a weighted average of the conditional probabilities, where the probabilities of each P of AI, where those are the partition elements, are the weights. Okay, so here's another problem for us to do. So according to the U.S. Census Bureau, 27.3% of U.S. women, adult women, have never married. They're called single. 49.8% are married, and 22% are widowed, divorced, or separated, and we call that category other. So of the single women, 6.7% are unemployed. Of the married women, 2.6% are unemployed, and the other women, 4.9% are unemployed. What's the probability that a randomly selected U.S. Adult woman is unemployed? Well, you see, these are disjoint sets, so we have a partition of all of the U.S. adult women. And so we have these events, and these are the probabilities, and these are the probabilities of each of those events happening, the size of the sets, and this is the probability you're unemployed when you're in each one of those disjoint sets. So according to the law of total probabilities, we have this expression. We plug in numbers and we get 0.042. So that's the probability that a randomly selected U.S. adult woman is unemployed. We will continue this discussion in 9.1.